This is lecture number 2 for IE4355 Facilities Planning, lecture 2, part 2 on flow and activity relationships. And as always, we start our lecture reading through the objectives for this class. The first one is to develop an understanding of the principles of facilities location, layout, and material handling systems, and to practice designing facilities. And in this lecture, we're going to be learning some methods and algorithms that are related to this first objective. Learn formulation models and analytical procedures for the study of facilities layout planning, which is also associated with this lecture. And learn fundamental principles of material handling. That's gonna come later this semester. And be able to design layouts, incorporating product, process, and personal requirements. In this lecture, we're gonna be looking at the activity relationships and the space requirements as the major topics. And the learning objectives are to understand the interactions between flow systems, flow, activity relationships, and space requirements as they relate to facilities planning. So let's start by discussing the topic on activity relationships. Measuring the activities among departments is one of the most important elements in the layout of departments. Basically, we want to take into account the flow between, let's say, departments or different areas in the company in order for us to determine where a office or where a particular department should be located in the floor. We want to take into account the activities because if there's a lot of communication or if there's a lot of movement between two departments, for example, then we want to be able to locate them close. So the travel distance is minimized and also the time consumed by moving from one department to the other is also minimized. So in this figure, that's what we are trying to illustrate with the arrows and the different colors is the activities and how those departments are, or what the activities that are connected to different departments. And in this figure, the colors have no meaning, but in general, we want to differentiate the arrows by the level of activity. So for instance, I can say in this figure, I can use pink to denote a high volume of activity, and green will mean something like low volume of activity. And then we can use that information to say, okay, if there's a high volume, then we want to make sure that these two departments, if possible, are located close to each other. So to evaluate alternative arrangements, activity relationships must be established. Activity relationships may be specified in a quantitative or qualitative manner. So we can use numbers or we can use qualitative elements to specify the relationship between those 2, 3, or I don't know how many departments, depending on the layout that we are designing. A chart can be useful in flow measurement. Is the mileage chart. So in this example, we have a mileage chart for traveling between two cities in the United States, and we have the cities listed in these horizontal axes and also in these vertical axes. And we want to illustrate here is the distance between these cities, which can be useful for multiple things. Like if you want to know, if you have a supplier in one of those cities and you want to send some of your product to any of the other cities, you can take into account distance, because the shorter the distance, the less fuel or the less time. So you can save from those two perspectives. So the idea here is like you list all these cities, and then you have the same cities here. So that's what's going to create these empty diagonal aces. So these two pieces of the matrix should be similar. Like for example, the distance between Atlanta and Boston is 1,037, which is the same distance between Boston and Atlanta, right? Same thing, Atlanta to Chicago, 674, Chicago to Atlanta, 674, and so on. So this is what is called, known as a mileage chart. When distances between two cities are symmetric, the mileage can be represented in a triangular mileage chart, which is what's illustrated here. So instead of having this triangular shape happening in 2 dimensions here, we can just create this type of graph. And it's very simple to use. You have all the cities listed in this vertical axis, and then you have a middle point that unifies those two cities. So in this case, Boston and Atlanta, 1,037 miles. But if I want to know, for example, from Dallas to San Francisco, then I can look for Dallas and San Francisco, and I can find that point in which both of those cities intersect. So that will be this point right here, 1,753. Another example, if I want to know between New York and Boston, then I can just find New York, find Boston, and then look at the intersection of those two. So that's 206 miles. So this is a triangular mileage chart. Quantitative flow measurements. Flows may be measured quantitatively in terms of the amount moved between departments. The chart most often used to record these flows is a front-to chart. And here's an example in figure 3. So again, we go back to this format of the mileage chart, but now we don't necessarily have a mileage measurement here. What we are quantifying is the flow, right? So in this case, those numbers are not going to be the same, even though you are looking at the same department. So there could be, if you're looking at 2 departments, let's say stores and stores here and miling, the flow from stores to miling might not be the same that the flow from miling to stores. So in this particular graph, in this particular from-to chart, we take into account the origin and the destination in order to quantify the flow. So that's what we have here. You can see that this side of the table, or this triangle, is not the same as this one anymore. What that is telling you is that the flow is not necessarily the same from one department to the other. So we are quantifying the flow. This could be, like, for example, the number of boxes that are moved from one department to the other, or the number of products that are moved from one department to the other. So these 3, what it means is that from turning, there are 3 units that are moved to miling. And this 7 right here, what it means is that from assembly, there are 7 units that are moved to warehouse. Very simple. Assembly to stores, it's just 1 unit. Plate to miling is just 3 units. Stores to press, just 9 units, and so on. So what are the steps for constructing a from-to chart? The first step is to list all departments down the row and across the column following the overall flow pattern. Then the second step is to establish a measure of flow for the facility that accurately indicates equivalent flow volumes. So that has to be a common unit. Like, for example, if you're using pounds to measure the weight, and that's the unit that you want to use to quantify the flow, then you have to make sure that the pounds are used for all the measurements. If you're quantifying the movement in terms of boxes, and there are different sizes of boxes, then you have to pick one size and then find an equivalent flow volume based on that type of box. So if there's a box that there's twice the size of a single box, and you are using the small box to represent the equivalent flow, then that means that for that large box, you have to quantify that as a volume of 2 boxes, and so on. So if the items moved are equivalent with respect to EC of movement, the number of trips may be recorded in the from-to chart. If the items move vary in size, weight, value, shape, and so on, then some common unit of measure may be established so that the quantities recorded in the from-to chart represent the proper relationships. Based on the flow paths for the items to be moved and the established measure of flow, you are going to record the flow volumes in the from-to chart. So here we have an example. In this example, we have a firm produces 3 components. Components 1 and 2 have the same size and weight and are equivalent with respect to movement. Component 3 is almost twice as large, and moving 2 units of either component 1 or 2 is equivalent of moving 1 unit of component 3. Thus, a movement factor of 2 is assigned to component 3. The departments included in the facility are A, B, C, D, and E. For this illustration, we assume that the departments are arranged in a linear flow pattern in the order of A, C, B, D, E. The quantities to be produced and the component routings are as follows. So we have component number 1 has a production of 30 per day, and as the example states, is a movement factor of 1. So the equivalent flows per day is 30 times 1, 30. And this is the routing for component 1. Goes first to department A, then goes to C, then goes to B, then goes to D, and then to E. Component number 2 has production quantities of 12 per day. There's a movement factor of 1 because it's also the same size of component 1, and we are using component 1 and 2 as our equivalent measurement. So the equivalent flow is going to be just the multiplication of 12 times 1, which is 12, and it has a different routing. So it goes to A, from A to B, from B to D, and then from D to E. And then we have component number 3, has production quantities of 7 per day, but this one is twice the size. And as we stated in the example, it's twice as large, and moving 2 units of 1 or 2 is equivalent to moving 1 unit of component 3. So in this case, the equivalent movement factor is going to be 2, because this is twice the size of component 1 and 2. And the equivalent flow is 14, 7 times 2. And this is the routing, A, C, D, V, E. And you'll see why the routing is important. Because now we want to create this flow 2 chart from 2 chart, and we're gonna take that into account. So let's start with component 1. So component 1 goes from A to C first. So I'm gonna go here and say, okay, from A to C, number 1, the flow is gonna be 30, right? So you're moving 30 units per day from A to C. Then you move those 30 units from C to B. So go find C to B is also 30. And then we go from B to D, also 30. So from B to D, component 1 is also 30. And then from D to E is also 30. So D to E for component 1 is 30. Okay, so we are done with component 1. Now we're going to repeat the process with component number 2. So I'm going to use a different color. So for 2, we go from A to B and we move 12. So from A to B, we move 12. And then from B to D, we also move 12. So from B to D, number 2, 12 units. And then from D to E, number 2, we move also 12 units. So now we are going to consider component number 3, another color, green. So we go from A to C. So this is component number 3. So for component number 3, we have 7 units. But as we explained already, that has a movement factor of 2. So even though we're moving 7, that represents an equivalent flow of 14 because of the size. Okay, so this is going to be 2 times 7, which is 14. And then we move to C to D. So from C to D, same thing. Number 3 is 2 times 7, which is 14. And then from D to B, 2 times 7, 14. And then from B to E, 2 times 7, 14. Okay. So at this point, we just have to sum those locations or movement that have more than one product. We had to find the total for those. So I'm going to change the color here to black. So in this case, from A to C is going to be 30 plus 14. So this is 44. For this one, this is 12. For this one, this is 30. For this one, this is 14. For this one, this is 42. This one, this is 14. This one is also 14. And this one is 42. So all of the other that has no values, then we can just say this is 0, 0, 0. This one is also zeros, 0, 0, 0, 0, and then 0 here, 0, and 0. So that's our from to chart for this example. So we just discussed a way to measure quantitatively the flow. Now we are going to look at a way to qualitative way to measure the flow. And as we mentioned already, flows may be measured qualitatively using the closeness relationship values developed by Method and given in table 1. So these qualitative relationship values are very important for things such as, let's say you have a department that needs to be close to an exit, right? Or to a dock for getting the trucks close to it so you can get the materials in a fast way. So those type of things can be specified using these relationship values. So if you have that type of need, like you need to have this department located close to a door, then you can use that A value that say this is absolutely necessary. Another example could be, let's say you have a department that produces a lot of noise, and you have a department that is an office that you would like to have the offices located way distant from this department that has a lot of noise. So in that case, you can use an X relationship value in which you say, okay, this is not desirable for this for these two. So that's the idea. I mean, again, those are not relationship that, or that's not the type of thing that you can define using a number. Is more a qualitative characteristic. So qualitative flow measurement, the values may be recorded in conjunction with the reasons for the closeness value using the following relationship chart. So this is, so what I'm showing here is, this is a relationship chart. And as you can see, we have all these departments listed in a vertical way. And all this is defining a department, sales department, personnel, plant manager, plant engineering office, production supervisors, controller office, purchasing department. And if we are trying to define the relationship between them or whether or not they should be located close to each other using this qualitative way of measure, we can have this format in which we have the diamond divided in two, and we can locate at the top of the diamond the importance of relationship, and then at the bottom we can state the reason. The reason can be stated using code, and there are 6 different codes that can be applied. So these are the codes, the reasons. So code 1 says frequency of use high, frequencies of use medium for number 2, and so on. And then 3 of them are based on use, and then 3 of them are based on flow of information. So the idea is that we can use this to formatted values to define the relationship between the departments using the relationship chart. So if we, for example, look at plant engineering office and production supervisor, this is going to be the way it is defined. So I means it's important, and 4 is the information flow between those two offices is very high. So we want to make sure that that is a combination or two pairs of offices that needs to be close to each other. And then let's see if we can find an A in this relationship chart. So I see a lot of U's, which means that it's unimportant, but I'm not, here we go. So we have A here and A here. So the plant manager has to be close to the plant engineering office, and same thing, plant manager has to be close to the production supervisor. And the reason for that, again, is information flow is high. Now let's see if there's a next in this chart. I don't think there's an X here, but again, that is for not desirable. And I provided you with the example in which, for example, you have a lot of noise in one department and you want to avoid having, let's say, offices close to that. Or let's say there's a room with chemicals and you want to keep also the people apart from that. So that will be another reason to use this code. Qualitative flow measurement, difference between relationship values U, which is unimportant, and X, undesirable. Two departments can be placed adjacent to each other with a relationship value of U. Two departments cannot be placed adjacent to each other with a relationship value of X. And there could be many reasons: environmental, safety, or facility constraints. A relationship chart may be constructed as follows. First, you list all the departments on the relationship chart. And 2, you conduct interviews or surveys with persons from each department listed on the relationship chart and with the management responsible for all departments. Number 3, then you define the criteria for assigning close-knit relationships and itemize and record the criteria as the reasons for relationship values on the relationship chart. Number 4, you establish the relationship value and the reason for the value for all pairs of departments. And number 5, you allow everyone having input to the development of the relationship chart an opportunity to evaluate and discuss changes in the chart. Okay, so now let's talk about space relationships. The most difficult determination in facilities planning is the amount of space required in the facility. The facilities planner then has the difficult task of projecting through space requirements for the uncertain future. In manufacturing and office environments, space requirements should be determined first for individuals' workstations. Departmental requirements should be determined based on the collection of workstations in the department. In terms of workstation space, workstations include space for equipment, materials, and personnel. So in this example, we are showing a workstation, and this is for a manufacturing space in which we have some machines And then we have also the space for the operator. And then we have some space for the materials or the product that is being worked on in this workspace. Once the space requirements for workstations are determined, the space requirements for each department can be established. Ensure that operational interference are not created by simply combining areas needed by individual workstations. Additional space is required within each department for material handling within the department. And then we have also to consider space for aisles. So here in table 2, we have some aisles allowance estimates based on the largest load. So if the largest load is less than 6 feet square, then the aisle allowance percentage is 5 to 10% of the total department area. And so on. As we increase that, then the aisle allowance should increase as well. Okay, so that concludes this lecture, part 2, and we discuss activity relationships and space requirements.